Okay, let's dive in. For, gosh, decades now, astronomers have been looking at the universe, doing the math, and, well, coming up short, like really short.
Hmm,
It seemed like about half of all the ordinary matter, the basic stuff, stars, planets, us was just missing. It wasn't where our model said it should be.
that's exactly right.
Mm.
It was this really fundamental cosmic puzzle. We had a pretty solid handle on the total amount of baryonic matter, that's protons and neutrons, based on measurements from the early universe, things like the cosmic microwave background.
Right, the echo of the Big Bang.
Exactly.
Hmm.
But then when we looked around today and added up everything we could easily see, stars and galaxies, gas clouds we could detect, it only came to about half of that expected total.
So, not just a small discrepancy, a huge chunk of the universe's basic ingredients just vanished from the books. The missing baryon problem.
Precisely. It had to be somewhere, right? It couldn't just disappear.
Yeah.
But it wasn't in the bright, obvious places.
And now it looks like we might have actually found it, or at least found where most of it's been hiding, thanks to these really weird, incredibly fast signals from deep space. Fast radio bursts.
Yes, exactly. FRBs.
Mhm.
A major study, this one led by folks at the Center for Astrophysics, Harvard and Smithsonian, and Caltech too, has used these bursts to finally put a pin in the location of a huge slice of that missing matter.
Okay, so that sets up our mission for this deep dive then. We need to unpack how these fleeting cosmic flashes basically played detective, revealing where the universe stashed its missing parts, and why figuring that out is such a big deal.
Absolutely. And FRBs themselves are, well, they're pretty amazing phenomena even before you use them for this.
Yeah, tell us about them. What are they?
They're these incredibly short, like millisecond long, but intensely powerful bursts of radio waves, brighter than entire galaxies for that tiny instant.
Milliseconds. Wow.
And crucially, they're coming from extremely far away, often billions of light years.
Billions. Okay, so that signal has traveled across a vast stretch of the universe to reach us. What happens to it on that epic journey?
Ah, see, that's the key. That's how we find the missing stuff. As that FRB signal flies across the cosmos, it passes through the incredibly thin gas that fills the space between galaxies.
The intergalactic medium, right, the
Yeah,
IGM.
that's the one, the IGM. Now, even though this gas is ridiculously diffuse, it's still made of those baryons, those particles, and it has free electrons. These electrons interact with the radio waves passing through.
Okay, so the gas, it leaves a fingerprint on the signal somehow.
It does. Specifically, it slows down the radio waves, but, and this is the clever part, it slows down the lower frequency waves slightly more than the higher frequency waves. It's a phenomenon called dispersion.
Ah, okay, so lower pitches arrive a tiny bit later than higher pitches.
You got it. So when the burst hits our radio telescopes, we see the high frequencies arrive first, and the low frequencies lag just a fraction of a second behind.
Like running through treacle versus air, the treacle slows you down more. And the amount of that delay tells you how much gas it traveled through.
That's a perfect analogy. The
Right.
bigger the delay between frequencies, what we measure is the dispersion measure, the more free electrons the signal encountered along its path. And since those electrons trace the gas,
You can weigh the gas column between us and the burst.
exactly, you can effectively weigh the amount of intergalactic material along that specific line of sight. It's incredibly elegant.
So how did this particular study use that technique? Did they just look at one or two bursts?
No, they need a good sample. They analyzed data from 60 different fast radio bursts. Each one gives you a unique path, a different skewer through the cosmic web.
60 different lines of sight. I guess that helps average things out and get a more global picture.
Absolutely crucial. And they weren't all the same distance either. The study included FRBs from relatively nearby, like one just under 12 million light years away.
Practically next door, cosmically speaking.
Right. And others that were incredibly distant. One, FRB 223051b, originated about 9.1 billion light years away. So its light started traveling when the universe was much younger.
Okay, so they're sampling different distances, different directions, covering a huge range of cosmic time and space.
Yeah.
So 60 cosmic skewers through the universe. What did weighing the gas along those paths reveal? Where was the missing stuff?
The big finding, the headline, is that the vast majority of the universe's ordinary matter isn't locked up in galaxies like we thought, or maybe hoped. It's out there, in the intergalactic medium.
Out between the galaxies. How much?
Their measurements point to roughly 76%. 3/4 of all the normal matter in the universe is spread out in that incredibly diffuse gas filling the voids.
76%.
Ju-
Wow, so it wasn't really missing, it was just hiding in plain sight, but incredibly spread out, like trying to find a faint mist in a giant stadium.
That's a good way to think about it.
Yeah.
It's not in bright, concentrated clumps like stars or dense gas clouds, which is why our usual telescopes struggle to see it directly. These FRBs gave us a way to feel its presence, to weigh it.
Okay, so if 76% is in the IgM, where did this study place the rest of the baryonic matter?
Well, the next biggest chunk, about 15% according to their analysis, seems to be in the extended halos of gas that surround galaxies. These are like big, tenuous atmospheres stretching far beyond the visible stars.
Right, the galactic halos. Okay, so 76 in the IgM, 15 in the halos. That leaves
less than 10% for everything else, the stars, the planets, the cold gas within the main bodies of galaxies, the stuff we traditionally think of when we picture the universe.
So this isn't just finding a bit of lost gas. This is like a complete inventory, a new cosmic census of where all the normal matter actually lives.
That's precisely why it's such a landmark result. And what's really satisfying, scientifically speaking, is that this breakdown, the 76%, the 15%, the rest, it matches incredibly well with what our best cosmological simulations predicted.
Wait, the computer models already suggested this kind of distribution?
They did. Advanced simulations that model how structure forms in the universe, considering gravity, dark matter, dark energy, gas physics, they consistently showed that most baryons should end up in this diffuse intergalactic state.
So this isn't just a discovery, it's a massive confirmation. It means our big picture understanding of how the universe evolved is actually on the right track.
It's a huge validation. It tells us those complex models are capturing something fundamentally true about the cosmos. We simulated it, and now, thanks to FRBs, we've effectively observed it. It means we can pretty much say the decades-old missing baryon problem is, well, solved. Case closed.
Closing such a long-standing case must feel pretty good. But it also, I imagine, opens up new doors.
Oh, absolutely. Now that we know where the baryons are, with this kind of precision, we can really start refining our models of how galaxies themselves form and grow.
Though so.
Well, we can better understand the whole ecosystem. How do galaxies pull in fresh gas from the IgM and their halos to fuel star formation? How do events within galaxies affect that surrounding medium? It gives us the context.
That actually raises a question for me. If gravity pulls everything together, why is so much gas still hanging out between galaxies? Why didn't it all just fall into them over cosmic time?
Yeah, good question. Gravity is definitely pulling inwards, trying to accrete matter onto galaxies, but there are powerful forces pushing back outwards.
Pushing back? Like what?
We call it cosmic feedback. Think about the immense energy released by supermassive black holes at the centers of galaxies when they feed.
Right, those huge jets you see sometimes.
Exactly. And also the collective punch of many massive stars exploding as supernovae. These events are so violent they can literally blast gas right out of a galaxy's gravitational grip and into the IgM.
So it's this constant battle. Gravity pulls gas in, black holes, and supernovae blast it back out.
That's a great picture of it, the cosmic tug-of-war. The source material even calls it an efficient cosmic thermostat, sort of regulating how much gas stays in a galaxy versus how much gets expelled.
And these FRB results, by showing so much gas is in the IgM, confirm that this feedback, this outward push, must be really effective.
Extremely effective, yes. The observations support the idea that this feedback is highly efficient at driving gas out of galaxies and populating the intergalactic space. It prevents galaxies from just growing bigger and bigger indefinitely.
Understanding that balance and knowing where all the matter is distributed must change how we think about the universe on the largest scales, too.
It absolutely does. It gives us crucial insight into the formation and evolution of the cosmic web, that huge network of filaments and voids that structures the universe. And it affects how we interpret light from distant objects, because that light has to travel through all this IgM gas.
It really feels like this FRB technique is just getting started. This study used 60, which sounds like a lot, but
it's really just the beginning. The researchers themselves talk about entering a golden age for this kind of FRB cosmology.
A golden age. I like the sound of that. Why golden? Are we expecting to find a lot more FRBs soon?
Oh, yeah. We're building next-generation radio telescopes right now. Facilities like the planned DSA 2000 array and SEORD in Canada, these aren't just aiming to find a few dozen more. They're expected to detect thousands of FRBs.
Thousands? Compared to 60, what does that leap in numbers let you do?
With thousands of lines of sight piercing through the cosmic web from all different directions and distances, you can move beyond just getting an average density. You can start to actually map the structure of the IgM in detail.
Like trace the filaments of the cosmic web.
Exactly. You could potentially map out where the gas is denser, where it's more tenuous, revealing the intricate filamentary structure of this hidden matter across cosmic time. It's like going from a blurry black and white photo to a detailed, full-color 3D map of the universe's backbone.
That's incredible. So just to sort of wrap our heads around this deep dive then, using these fleeting, powerful, fast radio bursts, scientists have pretty definitively found the universe's missing ordinary matter.
That's the core takeaway. It wasn't really missing, just hiding in plain sight, vastly spread out in the intergalactic medium, the space between galaxies, accounting for about 3/4 of all baryonic matter.
And nailing down that number, that location, doesn't just solve an old puzzle. It validates our big cosmological models and gives us powerful new tools to probe how galaxies and the cosmic web itself actually work.
Absolutely. It opens up so many new questions we can now start to tackle with much more confidence.
Which leads to a final thought, maybe for you listening. We're on the cusp of finding thousands more of these FRBs. Given what this first batch revealed, what other secrets might these cosmic messengers uncover about the universe's hidden structures? And how does knowing that most of the normal stuff isn't in galaxies like ours, but diffused across the vast intergalactic ocean, change how you picture our place in the cosmos?